GPS isn't a map. It's a whisper of a signal, weaker than the background noise of Earth, that keeps trillions of dollars, global power grids, and telecommunication networks in sync. A $30 device can crush it. Right now, this invisible clock is quietly failing. When it breaks, the world doesn't lose location. It loses shared reality. Everyone thinks they know what GPS is. You open your phone, you see a blue dot on a screen, and you trust it. You think it is a map. You think it is an unbreakable, invisible grid suspended in the sky, a permanent global utility guiding everything from your late-night food delivery to a commercial airliner. But you are wrong. GPS is not a navigation system. It is the synchronization layer of modern reality. And right now, it is quietly, systematically breaking down. Picture this. Somewhere over a geopolitical hotspot, a commercial airliner suddenly veers miles off its designated flight path, its instruments perfectly calm, but entirely compromised. At the exact same moment, an algorithmic trading desk on Wall Street registers a microsecond timestamp error, triggering a sudden, unresolvable cascade of arbitrage failures. Across the globe, in a bustling metropolis, cellular networks begin inexplicably dropping calls, unable to hand off basic data packets between towers. These are not isolated glitches. They are not random technological hiccups. They are symptoms of a crumbling foundation. Here is the reality. When you connect to GPS, you are not downloading a map. You are listening to a clock. And the signal carrying the time of the world is fragile. So incredibly fragile, in fact, that by the time it reaches the surface of the Earth, it is weaker than the ambient background noise of our planet. We are running a 21st century hyper-connected civilization on a signal that can be drowned out by a device you can buy online for the price of a cup of coffee. When this system fails, we don't just lose our coordinates, we lose our shared reality. Let me explain. To understand the catastrophic risk we are currently facing, we have to look at the mathematical blueprint of how this actually works. Global navigation satellite systems, whether it is the American GPS, the European Galileo, or others, rely on an architecture made up of three critical segments: a constellation of satellites in space, a ground control network, and the receiver inside your device. But the entire system is built on one foundational principle: the measurement of time. Your receiver is not looking for a location. It is listening for a highly precise time code broadcasted by atomic clocks on those satellites. By calculating exactly how long it took for those signals to reach you, your device uses a geometric process called trilateration to figure out where you are on the globe. But here is the engineering nightmare. By the time a GPS signal travels from medium Earth orbit down to your device, its power level drops to roughly negative 157 decibel watts. Let's put that number into perspective. That signal is exponentially weaker than a standard cell phone connection. It is a whisper in a hurricane. To even detect it, your receiver has to use complex mathematical correlation algorithms just to separate the GPS signal from the natural electromagnetic noise of the Earth. This inherent physical weakness is the root cause of our current vulnerability, and it exposes the system to three distinct vectors of failure. The first is jamming. This is the brute force approach. Because the GPS signal is so weak, it is incredibly easy to overpower. A low-cost, easily accessible radio frequency emitter can simply shout over the whisper, physically crushing the signal. We are seeing a global rising trend of these incidents. The U.S. Cybersecurity and Infrastructure Security Agency, CISA, explicitly warns that GNSS signals are highly vulnerable to jamming, classifying it as a massive risk for critical infrastructure. The second vector is spoofing. If jamming is a shout, spoofing is a lie. A spoofing attack doesn't just block the signal, it injects a false reality. It broadcasts a fake GNSS signal that is slightly stronger than the real one. Your receiver accepts the new data because the math looks correct. It accepts a true but poisoned reality. This is exactly why the International Civil Aviation Organization, the ICAO, now officially classifies GNSS interference as a severe flight safety hazard. Pilots and air traffic controllers are increasingly forced to rely on alternative procedures because their instruments are being fed alternate realities. But the third vector is the most terrifying. It is the blind spot. Time corruption. Most people don't realize that the world's critical infrastructure does not use GPS for location. It uses it for time. According to the National Institute of Standards and Technology, NIST, modern digital networks are fundamentally built on synchronized time distributed by GPS. Financial markets, telecommunications networks, and energy grids require nanosecond precision. They rely on something called the Precision Time Protocol, or PTP, to keep disparate networks in perfect harmony. But NIST confirms that PTP cannot stand alone. It is deeply dependent on a GNSS reference to maintain that accuracy. So what happens when a telecommunications base station or a power grid loses that master time signal from the sky? It enters what engineers call holdover mode. It relies on local internal clocks, but local clocks drift. They lose their perfect rhythm. And when the time drifts, the system stops being a navigation problem. It becomes a coordination collapse. If the power grid loses phase synchronization, you don't just get a software glitch, you get physical damage to infrastructure. If financial algorithms lose their microsecond timestamps, the sequence of billions of dollars in high-frequency trades becomes unresolvable. The system does not vaporize instantly. It degrades, it drifts, and then the dominoes fall. We have now entered an era where GPS is no longer just a technology, it is a geopolitical dependency layer. Look at the asymmetry of this warfare. On one side, you have a multi-billion-dollar, highly complex satellite infrastructure. On the other side, you have a cheap, readily available jamming device. This asymmetry has created a new economy of strategic vulnerability. CISA does not mince words regarding this threat. They classify GNSS dependency as a critical infrastructure vulnerability that can trigger cascading failures across multiple sectors. When GPS degrades, location fails. Then, time fails. Financial systems lose their sync. Telecom base stations begin to drift. Energy grid coordination diverges. What we are looking at is not the failure of a single tool, but the desynchronization of an entire digital civilization. And the players who understand this game are already building the next reality. We are witnessing a massive, systemic pivot toward a hybrid, multi-layered architecture. The era of trusting a single, weak signal from space is over. To survive the coming desynchronization, systems must be rebuilt from the ground up, creating a terrestrial backup. The United Kingdom government, for example, is actively evaluating terrestrial backup systems like ELORAN. This is a low-frequency, ground-based navigation and timing alternative designed specifically to provide a resilience layer when GNSS goes dark. The goal is simple and urgent: eliminate the single point of failure. Meanwhile, the European Space Agency is heavily pushing the Galileo High Accuracy Service, HAS, aiming for centimeter-level accuracy entirely independent of the American GPS. GNSS is no longer just about knowing where you are. It is a battleground for geopolitical infrastructure and technological sovereignty. Accuracy plus independence equals strategic power. In this new macroeconomic landscape, there are clear winners and losers. The winners will be the nations and corporations that build multi-layered positioning, navigation, and timing architectures. Capital will violently flow toward companies developing anti-spoofing technologies, timing security protocols, and advanced independent sensor systems that do not rely on external signals to know where they are. The losers will be anyone still operating under the illusion that GPS is a foolproof, secure utility. Single GNSS-dependent infrastructures and networks that outsource their synchronization entirely to the sky will face catastrophic liabilities. We are rapidly moving toward a world where you cannot trust the sky to tell you what is real. When the signal drops, the problem isn't that you are lost. The problem is that modern society stops sharing the exact same reality at the exact same time. And the most critical question you have to ask yourself in the next decade is this: what happens when a system loses not just its place, but its time?